Nice to see all of you. Those of you who I haven't met, I hope to run into you during the lunch break. I'll be around all day today and tomorrow. I just wanted to, let's see whether this thing is working here. Okay, you got to push it in the right direction. I was pushing it backwards, and that was the first slide. Anyway, so I'm sure everybody knows about deep learning, right, in this crowd, right? And one of the things that you might not appreciate is that it's actually huge, but it's limited to cloud applications. Or in your Tesla, you've got something like a 40 teraflop GPU behind the dashboard. And so it takes a lot of compute. And of course, that's just running the network. All the training still happens on the cloud. And so one of the challenges now is trying to deploy deep learning everywhere. And of course, we would like to be much more efficient, use a lot less energy, and so forth. And but there are certain constraints that we have to meet to do that. And these are driven by backprop, which is the learning algorithm that's used to train these networks. And it's powerful because it can train networks that are deep in space and time by discretizing space into layers. Those are the layers of your neural network. Or discretizing time into steps. Those are your time steps in a recurrent neural network. And it also requires that the output of each unit in the network be differentiable with respect to its inputs, because you use the chain rule to basically figure out how a change in the outputs is going to be accounted for by a change in a particular weight, so that you can change the weight in the right direction to minimize the error. And if you look at these constraints, they are very different from the constraints that we have in the physical world. For example, in the brain, or in fact, if I'm a hardware guy and I'm building stuff, I can build a lot of stuff that doesn't satisfy those constraints. Basically, with these constraints, I can't take advantage of physical space. It's continuous. And in a network, it's discretized into layers. And I can't take advantage of real time. Time is continuous. Things are playing out continuously in time, but I have to discretize that into steps. And I can't take advantage of non-differentiable signals, for example, spikes, which is in the title of my talk. And because they are not differentiable, they are basically discontinuous signals that if you differentiate, you get something that's infinity. And so if you look at the brain, it's actually taking advantage of all these things: continuous time, continuous space, and spikes. And it turns out that it's much more energy efficient than what we can build today. And so how can we relax these constraints? Okay, one of them is basically we should separate the physical level from the functional level. So when we train a backpropagation network to do some function, we think of those discrete time, discrete space, and so forth as functional abstractions. And when we implement something in hardware, we have our own abstractions that we like to work with in hardware. And then we can basically come up with a way of mapping these backprops abstractions onto the abstractions that are easy to implement in hardware. We do the same thing with computers, right? Nobody programs the computers by writing zeros and ones. We write Python and so forth, and then we automatically compile down to those abstractions. Early computers, people tried to build something in base 10, and that multiplier was really big, so they went to binary, which was a much more efficient way of implementing stuff with Boolean logic. Okay, so basically we are used to that, having these different abstractions. And there are already two existing examples of this mapping, algorithms, or they are called frameworks. One of them is the neural engineering framework, which was described in this book that came out in 2003. And more recently, there's something called the predictive coding framework. The work that I'm going to describe that we've been working on for the last 5 years has been in collaboration with Chris Elias-Smith, who came up with this framework as a way of mapping these sort of functional abstractions onto spiky neural networks. And we are now working on using this new approach here, which I'm not going to have time to talk about, but it's actually got some very nice, much better scaling properties. And so what's the payoff if we're able to do this? Basically, separate these levels of abstraction, use an abstraction that's more friendly to the hardware. Well, everybody should be familiar with this slide, right? This is, what you describe. One layer of neurons, n neurons connected to another layer of n neurons by n-squared connections. That's your classic layer-to-layer connectivity in a neural network, and this is what you train with your backprop. backprop tells you the weights with which each neuron is connected to the others. And so what you do is, if this neuron is active, you multiply that activity by some weight of that link, and you deliver that as input to the next unit. And the fact that time is discretized is that you wait each time step, you do this update for all the neurons, okay? And that's what's happening in your traditional neural network implementation. And so you can write down the energy that you expend for an update by the number of neurons that are active, the number of connections per neuron, and the energy that it takes to do this multiply accumulate operation, okay? And now, how does energy efficiency come in? This is normally what you do. This is the default way that you do the compute. So like a tensor processing unit has a full-blown vector matrix multiply built into the hardware that does these kinds of operations. And GPUs also have these tensor type operations. And but it turns out that basically not all the neurons are active every time step. So N active can be a lot less than N. And you can actually specify your connectivity. People are beginning to explore this. I've been exploring this. So you can take advantage of spatial sparsity and temporal sparsity, which can really reduce your energy per update. So if you write it down this way, where P active is the probability that a neuron is active in a given time step, and P connection is the probability that there's a connection from a neuron to a neuron in the next layer, then you end up with an energy per equivalent synaptic operation, you can call it, which is P active times P con times E max. So if you are basically temporally sparse, your probability is 1/10. Your probability of connection is also 1/10. Your equivalent energy per synaptic operation could be 100 times less than what it costs to do a multiply accumulate, okay? And of course, you can't take advantage of any of this if you just hardwire your vector matrix multiply. You're going to do it no matter what, those n-squared operations, okay? So we've been exploring for a while architectures that can take advantage of this kind of sparsity, or actually optimize the thing to operate in this way, okay? And so let's talk about temporal sparsity for a little bit. So the idea of temporal sparsity is that, each time step, these are my levels of activity. It turns out that in this second time step, this unit and that unit had outputs of 0. That's where the 0, the axis is there. So it means that I didn't have to do anything for those guys. And so I've cut down my number of connections. I have to update from 16 to 8, right? So that's your temporal sparsity. I'm taking advantage of this number here, being half. And with spatial sparsity, the idea is that I could also have sparse connections. And so now if each unit here was connected to 2 instead of all 4, then I've cut down from 16 to 8 updates per time step. So that's a total of 8, from 16 to 4. So that's a 4-fold, improvement in energy efficiency. So what does this have to do with the brain? Can we learn from the brain strategies by which we can exploit this? Because, of course, the brain is doing this. And if you look at, the way that you represent signals for computation and the way that you can represent them for communication, you have a choice of either digital or analog to communicate with, or digital or analog to compute with. Before World War II, we were building these analog computers. They communicated with analog number of turns of a shaft. And hopefully Tom Lee will talk about this. This is a fascinating topic. And then they basically computed with gear ratios, which was like your gearbox. That was also an analog operation. So it was analog for communication, analog for compute. After World War II, with the ENIAC and UNIVAC and so forth, we went to this quadrant here where we switched digital, originally base 10 and now base 2, representation for computation. And also for communication, we are doing those things digitally, okay? Now it turns out that so far we haven't really explored the quadrant, the fourth quadrant here. But people have started to look at basically, people have started to look at that third quadrant, okay? Sorry, I went the wrong direction. Okay, that's right, yeah. Okay, that fourth quadrant is where the brain sits, okay? It communicates in a digital fashion. These are your spikes or action potentials. And it computes in an analog fashion. The spikes get converted to analog signals by the synapse, and then everything gets summed together, integrated in some nonlinear spatial-temporal way to produce another set of spikes. So that's your analog to digital conversion. And so people, yeah, what's the advantage of spikes, basically using digital communication? We're already familiar with that because all our communication is digital now. But spikes are a little bit different from your standard digital signal. Okay, what you have with a spike is basically, it's like an impulse. It just occurs at some particular time and it's gone. And the only information it carries is the time that it occurred. And this allows you to do something that's called event-driven operation, where you don't do anything until the spike occurs. And then you do the updates that correspond to that neuron, right? And so in this way, you can basically efficiently take advantage of these sparse operations, okay? You're not locked to a time step. If there are no updates, no spikes, you don't do anything, and you can sit there. And spikes, so long as the spikes are encoding the information efficiently, you can minimize the number of updates that you're doing. Okay, so that's the idea of spikes. It allows you to do event-driven operation. And this has started to become more mainstream now with Intel's Loihi chip. It's an all-digital design, but it's using spikes, and it's operating in an asynchronous way. So all the logic is asynchronous. There's no clock, and the spikes drive the operations. Okay, so I only do a multiply accumulate when I get a spike. And in fact, I don't have to do a multiply accumulate. I just do an accumulate because the spike is like a 0 or 1, right? Okay, so that's also simplified. And even before Loihi's chip, about 5 years ago, IBM had their True North chip, which was another example of this class of operation. And so, just to point out, the True North was designed by my former students who worked on the next thing I'm going to mention here. But okay, before I introduce that, I'll tell you a little bit about. Excuse me, I have a cold, so I apologize for the for the voice. I have to tell you a little bit. I didn't actually tell you the whole story here. The brain doesn't actually sit in this quadrant here. It actually sits a little bit. Oh, sorry. Okay, I'm going the wrong direction. It actually sits a little bit up there, right? Okay, so it doesn't use. Communication is not purely digital in the brain. It also uses analog communication. This is what dendrites do. Dendrites are extended structures. It's like a cable. And so an input could come into a dendrite as an analog signal. It can propagate over some distance. Okay, so that's analog communication. And it turns out that analog communication is much, much cheaper than digital communication, right? The smaller you make the signals you're communicating with, your energy goes like the voltage squared. So you can drastically reduce the amount of energy you're using. So that's very efficient. And so this is the next thing to explore here in optimizing these architectures. And so a brain-inspired kind of network will look more like this, where I have my neurons here. I'm communicating their outputs digitally to a bunch of guys here, which are sort of like equivalent of synapses. And then I'm putting those analog signals, I'm spreading them in this sort of cable-like analog way to other neurons. Okay, and so I'm getting my spatial sparsity with a smaller number of connections from here to here, and I'm getting my temporal sparsity by the spike-driven operation. And so these would be your axons, these are your dendrites, and these are your synaptic filters. Okay. And so that's the kind of architecture that we've been exploring, and we actually looked at that early on in Neurogrid, which we published in 2012 or so, but we started working on this project back in 2008, 2007, and more recently in Braindrop. And so I'm going to talk more about Braindrop, which is sort of the next generation architecture. This original Neurogrid was just exploring sort of more like biophysical type, cortical-like networks for the sake of modeling biology or understanding how the cortex would do certain operations. With Braindrop, we sort of married that architecture with a mapping framework so we can go from a functional level or something that you train with backprop and map it onto these spiking neural networks. Okay, so that's sort of going to be the main bulk of the talk. Before we get into that part, any questions at this point? Yes. Yes. Yeah, like Balaji said, we put everything in the kitchen sink into this forum, right? They're not necessarily connected in any way. Okay, we're just giving you a what we call is kind of like the miscellaneous session, you know? Yeah. But yeah. So I think actually yesterday there was some cybersecurity stuff as well, right? Which might get into encryption and things like that, which quantum networks are good for. But okay, so let's so let's say this is sort of a slide, I grew up in the days of like, when we had like vinyl and then we switched to CDs and we had FM radio and now we're streaming everything. And so I inherently sort of understand the difference between analog and digital. And when I try to explain to my students, they don't get it. They're like, what are you talking about? They've never gone through this kind of transition where there was a debate, right? Do I get a CD or do I get a vinyl, LP? And when is it going to be good? My first CDs, I actually modified them. I upgraded the capacitors, CD players, and the resistors because it wasn't sounding as good as my vinyl, and I was an audiophile. So it was actually a couple of generations, about 10 years before it started to catch up. But anyway, that's another story. So you were just new, just from experience, all this stuff. But, so I have to rely on my students to come on ways of explaining sort of the difference between analog and digital. And this is what some folk came up with. And so, he talks about, this is your iPhone. It's got a 4.3 billion transistor processor, a 10 watt-hour battery. And if you actually, we're all familiar with this, right? It goes for 8 hours and then, it poops out. And then we have to charge it overnight, okay? So if you calculate how much current each of those transistors passes to drain that battery in 8 hours, it turns out that it's about 1/10 of a nanoamp, okay? 10 to the minus 10. And so that's this number here, okay? And it goes for 1 day with each transistor passing 1/10 of a nanoamp. And this is a transistor characteristic, a thick oxide transistor in 28 nanometer. And you can see here that the current changes exponentially over, over a volt, and the threshold voltage is here. Then it starts going quadratic. And you can actually run these transistors down to 10 to the minus 16 amps. That's 1/10 of a femtoamp. And this is how long your battery will last if you actually did that. So if each of these 4.3 billion transistors run, this is sort of your analog mode. Digital is up here. On average, each transistor is passing that much. Run this. You could actually run your $4.3 billion chip for 4.3 billion transistor chip for, a millennium. Okay, this is the difference between analog and digital. Okay, there's lots and lots of electrons, and you could actually use much smaller currents and still have a ton of electrons. Electrons goes down 10 to the minus 19. Okay, coulombs. Okay, so that's what we are trying to tap into when we are building in this analog part of the equation. Okay, and so this is a work that we did. I'm going to sort of introduce sort of the idea of how you map these sort of abstract computations onto these spiking neural networks in the context of this robotic control example, because I think it helps people to see it within context of some application, although you may not be interested in this particular application. And so this looks something like that, where I have, these Q0, 1, 2 are the direction in which I want the tip of, are the orientation, the joint angles of the robot, okay? It's a 3 degrees of freedom. And these gamma 0, 1, 2 are the torques that I want to apply to those motors at those joints in order to move the tip of the robot along a certain vector. Think of it as applying a force in some direction to the tip of the robot so that it can write something, okay? And so I have this sort of 6-dimensional space, and I'm learning some mapping from those 6 variables to these 3 variables. And it turns out that, people like Osama Khatib have sort of solved this problem analytically. So you can write down equations that tell you basically what you have to compute to control the robot. And just to summarize these numbers, I'll use these symbols later. So D is the dimensionality of the input space, okay? N is the number of neurons I'm using. And this is sort of just like a, 1, 2, 3 layer network. And then these are the number of things that I'm controlling, okay? So, and this process where we encode these variables in the neurons firing rates is called the encoding process. And the process where we decode out from these neurons' activity what we are trying to compute, that's your decode process. Okay, so we're using those terms here. And just to give you a feel for it, the kind of thing we need to compute, like basically this talk here is a combination of 1, 2, 3, 4 nonlinear terms. The first one looks like this. It's the sine of Q0, which is one of the joint angles, and the cos of another joint angle times the force component in a particular direction. Okay, so there's a combination of like 5 of these terms just to control one talk. Okay, and so what we did was we implemented this whole controller on NeuroGrid. And what you're going to see in the video is that the controller doing its thing. So I'll just let it go. I'll show you a little bit of the okay, so this is supposed to be some artistic panning shot, but but yeah. So this is what it looks like. So this is the robot. It's moving around, and basically everything is sort of in this sort of virtual space here, where we are animating the robot based on the joint angles. The user is moving that green ball around, and the vector from the tip to where the user wants to go is being sent in. That's this force's direction. And it's getting the joint angles. And NeuroGrid has 5 populations of neurons, these 1, 2, 3, 4, 5 pools. You can see their spikes and their activity here. There's 256 neurons in each pool. And we've computed the right weights to connect and drive the motor so that it moves in that direction. And basically, it's tracking this ball very nicely. And so now, what is the challenge of doing this with analog? Okay, so one of the thing that's impressive about this demo is that we are actually using these analog neurons. And if you look at the actual transistors that I showed you earlier, and you look at not just one transistor, but 1,000 of them, you'll find out that there's actually a huge variability. So in this subthreshold region that we're operating in, there's almost a decade difference in current between transistors that have the same gate voltage. Okay, that's just your inherent variability because we're going through the exponential. In the above threshold regime, where most people operate the analog circuits but burn a lot more power, it's actually much tighter. Maybe it's like a 10%, 20% difference. And so we are dealing with that. That's what's impressive about that demo. If you look at the tuning curves of the neurons, in other words, how they respond to any one of those input variables, there's a huge range of responses across the neurons. And these are, we just sort of flipped X in this case. So there's a set of neurons that get minus X. And the way we deal with this variability is basically, or the way we compute the functions that we want from these tuning curves is basically your machine learning 101 trick. We have some desired function we're trying to compute, and we have a set of tuning curves, which are also functions of that same variable here. We can basically, we want to solve for a set of decoding weights that will basically give us f of x as a linear weighted combination of those tuning curves. And this is just a linear algebra problem that Stephen Boyd will teach you if you take his convex optimization class, and even more sophisticated ways to do this. And so that's your, basically you sample your f at all these different points of x, and then you basically put your tuning curves, the response of each neuron to the same points in x, as basically columns of this vector A, and then you want to solve, these are your decoders. And so you want to solve this, you can do pseudo inverse, which will give you those decoding weights. And basically, so like on Braindrop, what you get is something like if you use 3 neurons, you get that approximation to a sinusoid. And if you use 8 neurons, you get that approximation. And you get 10 or 30 of them, you get that. So you get better and better as you use more and more neurons. So you can burn more power as you want more precision. And so basically that part of the problem is solved. Okay, there's another challenge with using analog approach. And these guys who built this robot demo and all that experienced this when they took the robot out to NIPS for a demo in 2013. They had this whole thing set up. They drove up to Tahoe. They got all the robots working. They had the demo working really nicely, like I showed you in the video taken in the lab. And so people came out to see the demo, and they saw this robot moving, and people came around. They're like, wow, this is very interesting. And as more people crowded around the demo, the temperature changed, and the robot started to oscillate. And it started oscillating, and people were like, wow, this is really exciting. And more people came, and it started oscillating even more. And so this is why we build stuff. We actually learn. You're doing an experiment even when you don't want to. But so it turns out that these analog transistors are really sensitive to temperature. We could actually decode temperature from the neuron's activity with 0.2 degrees Celsius precision. Okay, and so I'll skip this slide, but this is the range of just for the same transistor. As I vary temperature over 50 degrees Celsius, my current can change by 1.5 to 3 decades. Okay, and so if you look at, there's things you can do to sort of control sort of the overall trend. But even when you do that, these are called bias generator circuits. Even if you do that, because of mismatch, you still have some residual change in temperature. So across a 40 degrees Celsius range, this is what the Braindrop neurons look like. Okay, and so it turns out that you can also use least squares approximation to minimizing the least squared error to solve this temperature problem, where you collect a set of tuning curves across temperature, and you redo your optimization over that whole set of tuning curves. And so, so this is what you get for like a simple function like this over, this is 256 Braindrop neurons over that temperature range, 40-degree temperature range. It's rock solid. The different colors are all falling on top of each other. For a quadratic, as you get more complex functions, then you get less temperature robustness. Okay, and you basically can increase the number of neurons to counteract that. So I have 2 minutes left. Okay, so basically, so that's Braindrop. That's what it looks like. It's that's the die, and then that's the package die, and that's the chip. And just to walk you quickly through, this is what's on the chip. And basically, if you zoom into the actual active part of the die, we've got basically this. I'll start from the neuron. This would be like a neuron circuit. This would be a synaptic filter circuit. That would be a spike routing hardware. It's a tree that routes spikes to and from the neurons. It's got this leave node circuitry, and it's got the node itself circuitry. And then, that feeds those spikes. So all the interface in and out of this is digital, just these spiking events. And so that's the data path. And then the weight memory is here, so we can flexibly allocate or take advantage of sparsity in the network, or divide this up into smaller pools and have them talk to each other. And the way that you program it, we collaborated with Chris Alasma's group. They have a great programming environment called Nengo, where you can just write Python code. You can also implement any nonlinear dynamical system that you want. So you write down describe what you want to do in terms of these dynamical systems, basically. And then each of these is implemented by a pool of neurons that's mapped onto Braindrop. That's what your Python code will look like. And then you can basically then look at your results, run that on the chip. And so you very quickly just talk a little bit about applications. Most of you are from industry, where I think this thing fits well, and conclude. And so I think this kind of approach can give you low power, energy efficient enough solutions to actually do learning at the edge. So what you should be thinking of is something like where instead of relaying the sensor data directly to the cloud, you have some kind of always on processing going on here. And I'm showing you my energy budget. I have about 500 microwatts of energy that I'm harvesting from the environment. And I'm showing you basically how much I'm using for each of these steps here, and showing that it fits. And basically, only when something interesting happens, basically, do you fire your radio and send an alert to the user, okay? And so I like to joke that now everything can have a nervous breakdown, okay? They can, but they'll be quiet most of the time, but occasionally you hear from them. And so that's basically where we think, and sort of as the first step to doing this, we implemented a delay line. So the idea is, can you buffer some history of a signal so you can recognize speech or a keyword or something like that? And so this is actually sort of the implemented as the dynamical system we can solve for. There's a 3-dimensional dynamical system, and we can decode out of this neuron population any delayed version of the signal that we saw over some history. And this is just showing that it's actually the 3-dimensional state is following the theoretical result exactly. And so at the end of the day, basically, we are still part of the way to sort of answering the full question. What you really care about is your performance or complexity of the task and what the energy scales like with respect to that. We're thinking that we may scale better than the conventional, but we've only solved part of the equation right now because it consists of the network design to solve the task, and then the hardware design, which will then map that network onto some energy to compute that. And so far we focused, I've talked only about this sort of hardware component here, which is proportional to this E update. And basically, we are getting a sparsity of 1 over SNR for time and D over N for space. And so I'm going to breeze through this explanation here, but basically Braindrop is doing something like 380 femtojoules per equivalent synaptic operation compared to 25 picojoules for true north and low E. And we're the first sort of spike-based neuromorphic approach to go below what a Tesla GPU is doing, which is about 2.5 picojoules per flop, okay? So thank you very much.